Let's continue our discussion of rational exponents. So recall that a raised to the m over n is equal to the nth root of a raised to the mth, and that's also equal to the nth root of a to the m. So the difference between these two is that here in the first one we are taking the nth root of a and then taking the power of m, or raising to the mth power. But in the next one we're first raising to the mth power and then taking the nth root of a. So the operations are interchanged. Now we often do this one first. We often take the nth root first and then raise to a power. But either way, this is true. If n is even, so if you have an even number in the denominator, the result that you get is always positive. And the reason is because if n is even, then you're looking at an even root, like a square root, or a fourth root, or a sixth root, or an eighth root, and by definition those are always positive. So it's a little tricky. When you work with rational exponents, you have to keep that in mind, that you're really looking at even roots when the denominator is an even number. So, for example, let's simplify. And here we're told, and the instructions are very important for these problems, that variables can be any real number, meaning variables can be positive or negative. So I have 64x to the 8th raised to the 1/2. And I notice that the denominator is an even number. And so first I'm going to take the root, right? So in this case it's the square root, and of course just raised to the first power, so it's just the square root. So this is equal to the square root of 64x to the 8th, and the square root is always positive. So the square root of 64 is equal to 8, and then for the exponential expression, you take the exponent and divide by the index. So 8 divided by 2 is 4, so we get 8x to the 4th. Now, the point to keep in mind is that because the denominator was even, the right-hand side has to be positive. Now, x to the 4th is already positive because when you take any number, positive or negative, and raise it to the 4th power, you get a positive. We don't have to worry about it in this problem. But keep in mind that sometimes the right-hand side has the potential to be negative, and then you have to think a little more about that. Like in this example, let's simplify. The variables can be any real number once again. So the first thing I note is that as far as my rational exponent is concerned, the denominator is an even number, and that means the result has to be positive. So I'm first going to write the square root, and then I'm going to raise to a power. So it's going to be the square root of x to the 6th, right? That takes care of the denominator, but then I have to raise it to the 3rd power to take care of the numerator. And that's equal to, let's see, the square root of x to the 6th is x cubed, because you take the 6 and divide by 2 to get 3. But then you have to take that and still raise it to the 3rd power, right? That's still on the outside there. And that's x to the 9th. Now notice that this right-hand side, right, if x was a negative number to the 9th power would still be negative. But that's not allowed because the denominator here is even. So to make sure the right-hand side is positive, we use the absolute value symbols around it, like so. So this would be our answer with the absolute value symbols, because the right-hand side has to be made positive when the denominator is even. Okay, let's try another one like that. Okay, we're asked to simplify, and once again we're told variables can be any real number. So I see my rational exponent, I see my denominator is even. That means at the end of the day, my result has to be positive. So taking care of this denominator, this is the 6th root, right, of this quantity, which is y plus 2 raised to the 6th power. Okay, and with exponents, we take the exponent and divide by the index. So 6 divided by 6 is 1. So I just get y plus 2 to the 1st, which is just y plus 2. Now the question is, does this right-hand side have the potential to be negative? Well, not if y is like negative 1, because negative 1 plus 2 is positive 1. But what if y is negative 3? Well, negative 3 plus 2 is negative 1, right? And this could potentially be negative, and because the denominator was even, we have to put the absolute value on the right-hand side. Okay, and this would be our answer. Okay, let's try another one. So once again, simplify. But in this problem, we're told that variables are positive real numbers. And that means you're never going to get an answer that's negative due to the variable. So you don't have to worry about the absolute value. So the instructions here are different than in the previous problem. Now in this problem I also noticed that the index is odd. Now when the index is odd, you don't have to worry about the absolute value anyway. It's only an issue with the index being even. So in this case, we're going to first take care of the root once again and then the power. So this is going to be the fifth root, right, of all of the base. So negative 243, x to the 15th, y to the 5. And don't forget, you still have to take all of that and square it. So whatever I get there, I've then got to square it. Now the difficulty of this lies with dealing with the 243. And if you're ever unsure if there's a perfect power hiding in that quantity, you can always take it and find its prime factorization. So let me write 243. I know that 3 goes into that. It goes in 8 times. Or sorry, make that 81 times. So it's 3 times 81. And then 81, of course, can be factored as 9 times 9. Right, this is all multiplication. And each 9 is a product of 3's. So this is 3. This 9 is 3 times 3. And that 9 is 3 times 3. So now we're going to write that in exponential form, right? I have 5 3's, so it's 3 to the 5th. That means I can replace 243 with 3 to the 5th. So I come back over here and I say let's replace that 243 with 3 to the 5th. Let's do it up here. So this becomes the, let's see, it's going to be still the 5th root, right, of negative, but now it's 3 to the 5th. And then x to the 15th, y to the 5th, and then the whole quantity still raised to the second power. And now I have the odd root of a negative quantity, and that gives me a negative. If this was even, if this was like the square root or the 4th root or the 6th root, and there was a negative here, this would not have been a real number. But it's a negative when the index is odd, like it is here. Okay, so then as far as 3 to the 5th is concerned, you take the exponent and divide it by the index. So 5 divided by 5 is 1. So we get 3 to the 1st, which is just 3. Same thing for the x to the 15th. 15 divided by 5 is 3. So it's x to the 3rd. And then for the y, let's see, 5 divided by 5 is just 1. So it's just y. And then the whole thing raised still, don't forget, to the second power. And then when we square that, let's see, we get negative 3 squared is 9, x to the 6th, and then y simply squared. And that would be our answer. Now, of course, we don't have to worry about the absolute value for the reasons we discussed in this problem. Okay, let's try another one. Okay, so this example illustrates that properties that we used, the properties of exponents still apply even when you have rational exponents. So for this problem, I'd like you to review the video, Properties of Exponents, Part 3. And in that video, I discussed the fact that when the base is a fraction, like it is here, and the exponent is a negative number, you can make the exponent positive by taking the reciprocal of the base. That is, I can write this as follows. 9x squared divided by 16 raised to the positive 3/2. So if you want to make the exponent positive, you can do it as long as you take the reciprocal of the base. Okay, then I'm going to deal with the 2, which is a radical, right, or a square root. So it's the square root of 9x squared. Whoops. 9x squared over 16. And don't forget, then you still have to raise it to the 3rd power. Now, when I wrote that, the first thing I actually noticed was that the index was even, right? And I know that when there's an even index, I have to make sure I get a positive quantity. But I'm already told in the instructions that the variables are positive. So I'm not going to have to worry about the absolute value at the end of the day for this problem because the variables are positive. So the square root of 9x squared over 16, that's going to be, let's see, 3x over 4, right? Square root of 9x squared is 3x. Square root of 16 is 4. Then I'll raise to the 3rd power. And then finally that's going to be 27x cubed. And then 4 cubed is going to be 64. And this would be my answer. Okay, let's try another one like that. Let's simplify 8 to the negative 2/3 times 8 squared. Now remember that when you have a to the m multiplied by a to the n, that's equal to a to the m plus n. So as long as you're multiplying these together and they have the same base, you add the exponents. And that's what we're doing here, right? These have the same base, so let's add the exponents. So it's going to be 8 to the negative 2/3 plus, and of course this is 2, right? Let's write it as 2 over 1. So I have to add these two fractions together. So I do that by getting a common denominator. Times 3 times 3. So I've got 8 to the negative 2/3 plus, and this becomes 6/3. So I'm looking at 8 to the, well, adding these fractions together, I get 4/3. And that can actually now be written as the cube root of 8, right? And then raised to the 4th power. Remember that 3 becomes an index. And the cube root of 8 is 2. And then I raise that to the 4th still, and I get, as my final answer, 16. Okay, let's try another one like that. Let's simplify x to the 2/3 times x divided by x to the 1/2. So once again, I'm going to multiply these together, and I do that by adding their exponents. So this is the same as x to the 1st. We can write that in if we want. So this is going to be x to the 2/3 times x to the 3/3 over x to the 1/2. So I wrote the 1 as 3/3 because I know I need a common denominator. I want to add these two exponents together. And when I do that now, I get x to the 5/3 divided by x to the 1/2. And now let's see. Do you remember what to do with these exponents? We subtract, right? So it's going to be 5/3 take away 1/2. Let's do that up here. So this is going to be x to the 5/3 take away 1/2. So all the properties for exponents are still holding. But of course, when you subtract two fractions, you need a common denominator, right? So it'll be x to the, well, top and bottom by 2 to get a denominator of 6. It's going to be 10 over 6. Take away, and top and bottom by 3. So it'll be 3 over 6. And I'm looking at x to the, it's going to be 7 over 6. Now that can be written in the following way. You can simplify this further. You can write that as the 6th root of x to the 7th. And that's equal to, well, it's going to be the 6th root of x to the 6th times x. And then you can break these apart. And the 6th root of x to the 6th is just x. And then times the 6th root of x. And this would be your final answer. Now, it's okay to stop at this point right here. But if you wanted to go further and simplify, you should write this. Now you might think, oh, don't you need an absolute value on this because can't the x be negative? Don't you have to ensure that it's positive? And the answer is no, because the original problem here was that we had x to the 1/2. And I know that from the original problem, x has to be positive. So I don't have to worry about x being negative down here. Okay, and that's how we work with rational exponents. Until next time.